Hello, everybody. This is Miss Carter. Hoping you have a good Thursday. We're going to go over a couple of things for today's assignment, as well as go over a couple of problems that I noticed and Miss Mills noticed on a previous assignment. Today, basically, the main thing we're going to be talking about are valence electrons. Valence electrons here, if you remember, we talked about at the very end of the what's now the school year, back in March. We were talking about the electrons that we find around the outside of the shell of an atom. The electrons, we said, if you remember when we were drawing Bohr models, you can put 2 on the first shell and 8 on all the shells after that. Well, that basically is what we're going to be looking at, but we're looking at just that last shell. And the reason we're looking at that has to do with how well those atoms like to join together, if they like to bond together or not. And it's all because of those valence electrons. Let's just go through these notes here briefly. The valence electrons that are in the highest outermost energy shell are called the valence electrons. So if you draw the Bohr model, they're the ones in the very last shell. And it can be anywhere from 1 up to 8. And let's see. That level is also called the valence shell of the atom and are held loosely to the atom. It's kind of like, if you think about it, like the planets of our galaxy. The planets that are closer to the sun, like Mercury, Venus, Earth, Mars, because they're so close to the sun has a tighter grip on them. And so it's harder for us to kind of get away from the sun. Whereas the planets on the outer edge, Uranus, Neptune, Jupiter, Saturn, those, and even some of the asteroids and comets and things like that, once they get away from the sun has less of a pull on them. Okay? And so the same thing is true for an atom. The electrons that are closer to the middle, to the nucleus, with the protons and neutrons, is kind of like being closer to that sun. Those electrons that are close have a tight pull on them. But the further away you get, the less it can hold on. Okay, and so those are held more loosely. The number of valence electrons in an atom determines the properties of the atom and the way the atom will bond chemically. We're going to look at a couple things with that when we look at the periodic table here in just a minute. All right. Next slide. And I'm going to be including these slides also on Classroom, so if you need to kind of refer back to any of these, you can. As a rule, the fewer electrons in the valence shell, the more reactive the element is. When a lot of you are doing your research for the elements, for the March Madness thing we did, several of you mentioned that, it was either very reactive or not reactive as part of their properties, but we didn't really go into what that meant. And so what it means is how likely it is to join up with another atom, okay? And so if it's got only a couple in its last shell, it's going to want to join up more easily than those that have more in it. Okay. When an atom has 8 electrons in the valence shell, it is considered stable and it will not join up with anything else. Occasionally, it might join up with another one of itself, but basically, they're going to be what's called stable, so they're going to not want to join up with anything else. They're going to be just like, leave me alone, I'm good, I don't need any other atom. Okay? So, some examples here you have the ones that are stable would be neon right here. And you can see here Ne being the symbol for neon. Its valence electrons are 8. If you remember, we did kind of something with these dots here too. The 2 dots here, 2 dots here, 2 dots here, 2 dots here means that there are 8 electrons in the outer shell of neon. Its atomic number is 10, 2 on the first shell, 8 on the second shell. So 8 on its last shell there means it's full, doesn't need any more. Then you've also got potassium here with its symbol of K. It's only got one little lonely electron there. So because of that, it is very active. It basically, it's like I said, that lonely electron wants to find a partner, and so it's going to be very reactive, wanting to join up with whatever it can. Okay, so potassium, very reactive. Now, the last slide on your notes page here is kind of going over exactly what the periodic table shows us. Okay, so I'm going to refer back to this in just a minute, but let's look at the periodic table itself first. All right, so if we look at group 1, okay, and if you remember from our discussions earlier, from your work earlier, group 1 is called the alkali metals. And so the alkali metals, everything here in group 1, all of those have only one electron in their last shell. Okay, and so because of that, that means that they are very reactive. Okay, the one of the most reactive of any elements out there. Okay, these guys love to join up with other elements. Okay, they are very reactive. So basically, by looking at the periodic table, if I were to ask you which elements were the most reactive, you simply just have to look, say, okay, well, everything right here, everything in this first column is going to be the most reactive because they only have one, they're going to want to join up. Okay, so that's why where things are placed is so important. Then, right next to it, you have the alkaline earth metals. These here, all of these have 2 in their last shell. Okay, so everything from beryllium down to radium, all of these have 2 in their last shell. So they're still going to be pretty reactive. Not as reactive as alkali, but still pretty reactive, okay? Because it's not going to take a whole lot of energy for them to give up those 2 electrons, okay, to kind of share them with another atom. Okay, so very reactive for the alkalis, somewhat reactive for the alkaline. Okay, then we're going to kind of skip over here in the middle for a second. If we go over to group 18, actually, I'm sorry, let's start at let's start at group 13 here. Group 13, which is known as the boron group. Okay, the boron group all have 3 electrons in their last shell. So they're somewhat reactive, but not near as much as these 2 over here. Then you've got the carbon, okay, carbon group 14 is going to be, again, they have 4 electrons in their last shell, so they're not really all that reactive. They might join up with others of themselves, but joining up with a lot of other elements isn't really their thing, okay, especially the bigger ones. Then we've got group number 15. Group number 15, which is the, if you can see here, let's kind of blow this up real quick. The Pinkogens, I'm horrible at saying that name, but this right here is that group name. We also have called it the nitrogen family, but this is the scientific term right there. This entire family, group 15, everything from nitrogen down to moscovium, they all have 5 electrons in their last shell. Okay, so still not going to be that reactive. Next group, group 16, the chalcogens, that is also known as the oxygen family, they all have 6 in there. So you're starting to get a little bit more reactive because they don't have to like steal or take as many atoms or as many electrons from other atoms as possible as they did before. Okay, so these are getting a little bit more reactive now. You're kind of going back the other way. And then you've got the halogens here. The halogens, let me scoot myself over there. The halogens is everything in group 17, and the halogens are all they all have 7 electrons in their last shell, and so they're going to again be very reactive because remember, in order to be full, you only need 8. So they basically need just 1 more. All right. So finding that lonely, remember, like potassium, that K, finding that lonely atom that has that 1 electron is going to be pretty easy for them. Okay, so they're going to be able to join up pretty easy. Okay, so halogens are one of the most reactive next to the, I can't get over there right now. Next to the alkalis, which was group number 1. Okay, and then finally the last group, group 18 right here, they all have a complete outer shell, with the exception of helium. Every single one of these has 8 in its last shell. Okay, so all of these have 8 in their last shell except for helium, which has 2, but it's still complete. Okay, because remember, it only has that first shell. All right, so just by looking at where it's at in the periodic table, we can determine how many valence electrons it has. Okay, we don't have to draw out the Bohr models. We don't have to do any math. We don't have to. It's just simply looking at the periodic table. Okay, if it's in this column, if it's in group 1, it's got 1. If it's in group 2, it's got 2. And then we skip this middle part here. If it's in group 13, it's got 3. Group 14, 4. 15, 5. 16, 6. 17, 7. 18, 8. Okay, which is what I have here. I'm trying to move myself there. Which is what I have here on this slide. Okay, it tells you basically just kind of an overview of what each of those is. Now, the one we didn't cover, the transition metals, which is that group 3 through 12, 3 through 12, they're going to have either 1 or 2. So that one there is a little bit of calculation with, but we're not going to really be worried about that much on those. Okay, so we don't really need to get into that yet. All right, but it's going to be either 1 or 2, one of the two. Okay. So that's how that all works together. All right, so hopefully that makes sense. If not, if I'm talking too fast, I apologize. Try and rewatch it, see if it makes sense after you look at it again. Then for today, the assignment that you have to go with it is kind of a practice to make sure that we understand what we're doing here with the valence electrons. This assignment is going to be done on Cami, and basically what you'll do is, and this will be submitted to you, you just go here to open with, maybe, no, it's not gonna let me right now. Okay, so anyway, you'll open it with Cami, just click on this and it'll come down with Cami, but oh, there it is. So you annotate with Cami, there it goes, and you're going to start off with oxygen, and you're going to basically look at how many valence electrons oxygen has. So again, we just look at it where it is in the periodic table, and we should be able to figure it out from there. And if this loads for me. Come on. Sorry, I should have had this open already. All right, well, while that's opening, let's go back to this. All right, so anyway, you'll start here with oxygen, and oxygen is either going to have 7 valence electrons in it or 6, okay? So if I go and look at my periodic table again, I find oxygen, which is right here, okay? And since it's in group 16 right here, oxygen tells me there are 6. So I go back here and I pick the 6th one. So I'm going to, on Cami, I'm going to draw with the highlighter or something else that would make a good colored mark. You draw from here to here. Let's see if it's open yet. And these directions are on there as well on the first page. All right, so basically what you'll do here is you'll just take the drawing tool and choose a color. And so I would go to oxygen, okay, or to 6, I mean, from oxygen, okay, which takes me to sulfur. So then I look up sulfur and I say, okay, how many does sulfur have? All right, so I find sulfur. Sulfur is right here, also in group 16, which means it will also have 6. And so I find 6, which is right here. And I continue like that to argon, okay? So basically what I'm doing, guys, is I'm just trying to figure out what is the path that's going to get me down here to Einstein, okay? So whichever one that element that you get to has, whatever valence electrons it has, is what you end up choosing on the arrow, okay? If you have questions or you're uncertain, please feel free to email either myself or Miss Mills. And hopefully you get it and hopefully understand. And I will talk to you again soon. Thanks for watching, guys.